So now we're ready to look at this process of estimating the area under the curve with these rectangles in a more general sense. Okay, so let's develop this. So we start with a function f that is continuous and positive, first of all, over the interval from a to b. And we're going to estimate the area under the curve in the following manner. Now, when we say continuous, remember there's no holes, jumps, gaps, and no discontinuities. Positive meaning its outputs are all positive, so it's always above the x-axis. For example, here's a graph of a function here. We'll call this the function f. This is continuous. There's no gaps, holes, or jumps, or vertical asymptotes or anything. And it's all above. We'll let this be the x-axis down here. Okay. What we're going to do is we're going to divide the interval, and let's say it goes from a to b. So let's say a is here on the x-axis, and b is here. Okay, so from a to b, we want to find the area under this curve. We're going to divide that interval AB into n subintervals. So in general, we did some examples in the previous videos where we had 4 subintervals or 2 or whatever. But here we're going to do it in general, just n. How would we proceed? Well, we're going to do equal width. So what would the width of each subinterval be, of each rectangle be? Well, we're going to use this delta x, right? Change in x, or the width for the width of each of these. And it's just simply the length of the interval here. And the length is going to be what? B minus a. Take the larger number and subtract the smaller number from that. B minus a. That would be the length here, right? So if I'm going from, say, -4 to 5, 5 minus -4 is 9 units wide, right? That's how the whole thing would be. And then we just divide it by n, the number of subintervals, and that will give us the width of each of our rectangles. Now the right endpoints, there's several ways we can denote them, and here's one way. The first right-hand endpoint is going to be, we'll say x of 1 for the first, in the first subinterval, x of 1 is going to be a plus delta x. Okay, now what do I mean by that? So here's a, which by the way we're going to call a x of 0. And we'll explain why we start with x of 0 here in a minute. And then here's x of 1, let's say. And so here's our first subinterval. What's the width? What's the distance between these two? From a to x of 1. That's the delta x. Right? That's the width we're talking about. X of 2. And again, this would be the delta x again. Right? And then an x of 3 and so on. Right? And that's going to continue, and that pattern will continue. Now b, that's going to be x of n. And therefore the one right before that will be x of n minus 1. So these are our endpoints. And so you can see on the first interval from x of 0 or a to x of 1, the right-hand endpoint is x of 1. Okay? And I can express x of 1 in terms of a, right? It's a plus delta x. A plus delta x. That's what I'll call it, a plus delta x. X of 2 is a plus delta x, or a plus 2 delta x. You see that? So what's x of 3 going to be? A plus 3 delta x. Okay? And x of n minus 1 will be a plus n minus 1 times delta x. And x of n is going to be a plus n delta x, but that's just going to be b. By the time we go through add all n of our distances, will be all the way to b. Okay, so that's the notation we'll use for our endpoints. We'll start at x of 0, and by starting with x of 0, we'll end with x of n. Okay, so if I have 4 subintervals, if n is 4, I'll go x of 0 to x of 1 is the first interval, x of 1 to x of 2 is the second interval, x of 2 to x of 3 is the third interval, x of 3 to x of 4 would be the last and fourth interval, for instance. Okay. Now, when we construct the rectangles for each subintervals, it's going to be the height determined by what? The right endpoint. So if we're going to do a right-hand approximation, then it would be the right-hand endpoint. So let me get a ruler here just to help with things. So the first rectangle here, the height will be based on the right endpoint. And so I'll come across at that height, and then back down. There will be my first rectangle. The second rectangle, x sub 2, use that height, will come up to that point on the graph. And then horizontally, right, across, and then back down. Here's the second one. X sub 3, right-hand endpoint. Right. And so there's the rectangles. That pattern is going to continue. Now when we get down to the last subinterval here, the right-hand endpoint is going to be b, or x sub n, right? So we'll get to that point, and then we'll come across here. If we want to do the one just before that one, we could do that one too, because the right-hand endpoint will now be here. We'll go up to that point. Okay, but and we're not going to draw them all, but that's the idea. So some, notice some rectangles are above the curve, like over here. Some are below the curve. But these are all right hand, right? Using the right hand endpoint of each interval to determine the height. Right, the height will be right on that curve at the right hand endpoint of each one. Right, so for this last one, we're going to use b, the height at b. Okay. Now, if we sum these rectangles to provide an approximation for the area under the curve, we'll call this the right-hand approximation. I think I've already mentioned that, and we denote it r sub n. So it's going to be what? F of what? The height of this first rectangle is f of x sub 1. That's the height of this rectangle. That's how high we come up, right? Because this is the curve of the function f. And the width is delta x, so f of x sub 1 times delta x. That's the area of this first one. The second one, f of x sub 2, right? The height of the second one, right-hand endpoint, x sub 2 times delta x. And so on, right? All the way down to the last one is going to be what? F of x sub n is the height of this last one, and the width is delta x. So I'm adding all those up, and you'll notice I can simplify a little bit because all of them have a delta x. I can factor that delta x out. And so here is an expression for the right-hand sum. We can also construct the nth left-hand approximation. I'm not going to draw it out, but you can imagine in that case we'll use the left-hand side to find the heights of each of these rectangles. Okay. In that case, the left-hand endpoints are going to be what? X sub 0 is the first one, right? So A is the first left-hand endpoint for the first interval. From x1 to x sub 2, then it's x sub 1, and then x sub 2 to x 3, it's x sub 2, and so on. The last one, the left-hand endpoint is x sub n minus 1. Notice we stopped at that one. Okay. And then what's the area going to be? Well, we take f of x sub 0 times delta x. That would be the first, right? Height of the rectangle at x sub 0. The width is still the same, delta x. F of x sub 1 times delta x, and so on. Right, factoring out that delta x, we get that. So very similar, but these are the two sums. Okay, now we want to use these sums now to write formulas for Rn and Ln in terms of n, so that I'll be able to generate, if you remember in the last video I was showing you those values, right, for a particular example, did this table of values, how did I get these values? Well, we can get a formula for these Rn and Ln's in terms of n. You can also do it for the midpoint that we talked about, but I'm a little more complicated to do that one. Okay. So to help us with this process, though, I want to take a little brief introduction for some of you, and some of you are familiar with what we call summation notation. So summation notation is used in mathematics to denote a sum, and so we use this symbol here. This is the Greek letter capital sigma. It's the Greek letter capital sigma, and it stands for sum. Okay, so this says sum what? The a, and then there's a little subscript I. This I is sometimes called the index of the summation. And this tells us that I is going to start at 1, and it's going to increment by 1 each time until we get to n. And then we're going to add all those things up. So in other words, we start at I equal 1. So a sub I, if I is 1, then I have a sub 1. Then I goes to what? 2. A sub 2. then I goes to 3, a sub 3, and so on, until I get to n, a sub n, and then I add all those things up. That's what it means. That's what it means. So for example, here's an example now. The a sub I now here is a function of I, okay? So when I is 1, and then we're going to go up to 4, what do we have? So when I is 1, I have 2 times I is 1 plus 1 squared. That's my first quantity, right? This is when I is equal to 1. And then when I is 2, replace I with 2, I get 2 times 2 plus 2 squared, right? This is when I is 2. And then when I is 3, 2 times 3 plus 3 squared. And then when I is 4. And I stop there because why? Because this number tells me where to stop. So I always increment by 1, and we just evaluate these things, and then we add them all up, right? If you do that, I'll let you do the math. You should get 50. Okay, so that sum is 50. Okay, so that's how we use summation notation, to write this long sum in a more compact way. Here's one more example. This one, I equal 1 to 6. I'm going to start I equal 1 and then go all the way to 6, incrementing by 1. But you look here and it's just a 5. There's no I. What if there's no index there? What does that mean? Well, 5 is the quantity. When I is 1, I have 5, right? When I is 1, I just have 5. And when I is 2, I have what? 5. And when I is 3, I have what? 5. And so on. I have how many 5s by the time I'm done? I equals 6. I've got 6 5s, right? So in other words, this is 6 5s. I could also write this as just 6 times 5, right? 6 5s is 6 times 5, which of course we know is 30. Okay, so this is summation notation. Now, some important relationships to know with summation notation is the following. If I have I equal 1 to n, and I have some expression a sub I plus another expression b sub I, then I can treat these as just the sum of the a sub i's plus the sum of the b sub i's. Let me illustrate that up here. I could have thought about this as, according to this relationship, I equal 1 to 4 of 2i, right? That would be like the a sub I here, and then plus bi, summation I equal 1 to 4 of I squared. I could have done that. And if I had done this one, then what do I have? I equal 1, I get 2. I equal 2, I get 2 times 2 is 4. I equal 3, I get 6. I equal 4, I get 8. Add all those up. And then here I get what? Squares, right? So I get 1 squared plus 2 squared plus 3 squared plus 4 squared. If I add all those quantities up, I'm still going to get 50. Still get 50. Another thing is, if you have a constant, C is a constant, times some expression, that constant can come out and I can do the summation and then multiply the constant. In other words, right here, I could have written this as 2 times the summation I equal 1 to n, sorry, I equal 1 to 4 in this case, of I. In other words, I can pull that out. I still have to have this one. Can't do anything with that. There's no constant multiple to pull out of that one. But I can bring, so now I just do 2 times what? 1 plus 2 plus 3 plus 4, right? That's what this is. In fact, we can write this out. So this is 2 times 1 plus 2 plus 3 plus 4, and this is plus what? We said 1 squared plus 2 squared plus 3 squared plus 4 squared, right? So if you add all that up, you're going to get the same thing. You're going to get 50. Okay, all of that. The last relationship is if you go from I equal 1 to n of c, just c, there's just a constant, then it's n times c. And we saw that here, right? Here, the n was 6, right? And the constant was 5. And we end up with what? 6 times 5, n times c. Right? Because you're just doing c, 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 add them all up n times. So these are important linear relationships, linearity properties of the summations, and you need to be familiar with those. Okay. Let's go in the opposite direction. Let's just write this expression in a summation notation. 4 cubed plus 5 cubed plus 6 cubed plus 7 cubed plus 8 cubed. Well, we start with the summation notation, and we have our index I, and where are we going to start with? Well, we start at 4 in this case, and end at 8, then I can just write this as I cubed, right? When I is 4, I get 4 cubed. And then we increment by 1, 5 cubed, 6 cubed, 7 cubed, 8 cubed. But that's not the only way. What if you said all the other ones we started with I equal 1? Could we start with I equal 1? Well, you could. To get I equal 1 to work, though, look what you have to do. You want 4 cubed. So the way to get 4 cubed is what? I plus 3. 1 plus 3 is 4 cubed. And then when I is 2, I'll get 2 plus 3, 5 cubed. When I is 3, I get 6 cubed. When I is 4, I get 7 cubed. When I is 5, I get 8 cubed, and that's where I need to stop. Okay? And so you can adjust the index to start at different values that will affect briefly this expression here. So I could actually do the summation in lots of different ways. I can start at I equal 1, I can start at I equal 4, I can start at I equal 2. I can do other things as well. Okay? But our purpose now is to use summation notation for our right and left-hand approximations. So here they are, if you remember. And so for the right-hand sum, I can write this in summation notation. And I'm going to do it this way. Summation I equal 1. And I'm going to start at 1 because it's x of 1. F of x of I. And then delta x, right? And I'm going to go what? I equal 1, 2, all the way up to what? N. Okay. Or if you want to, you can even, this delta x is a constant, I could pull this delta x out. Because there's no I with that delta x. Now if the delta x, was dependent upon I, then obviously we couldn't pull it out. And then similarly, left-hand approximation. This time, notice I'm going to do summation I equal what? I'm going to start at I equal 0, right? To what? N minus 1. Now you say, well, I don't like that. I like to start at I equal 1. You actually can start at I equal 1. And in that case, what's going to happen, though, is you're going to look at f of x sub I minus 1 times delta x. So when I is 1, 1 minus 1 is what? 0. You get x of 0. When I is 2, I get 2 minus 1, I get x of 1. And so on. So this is going to go all the way up, in this case, to n now, because when I plug in n, the last one, I get n minus 1. Get that one right there. Okay. So there is the notation that we use for those. Real quick, midpoint rule. It's a little more complicated. For the midpoint rule, the midpoints of the subintervals are to add the left and right hand endpoints and divide by 2. Right? That's going to get midway in between those two. And then the first and second for the second interval, and so on. Okay. And then the nth midpoint approximation is going to be this, right? F of this, right, first midpoint times delta x. So this will be the height of the rectangle. This will be the width. For the second rectangle, this is the height, this is the width, and so on. Okay. And so adding all these things up in summation notation, right, we can write it this way. This is starting at I equal 1. Notice if I equals 1, I've got x of I minus 1. So when I do plug in 1, 1 minus 1, I get x of 0, and then x of 1. So I get that first one. And I end at n. Notice if I plug in n, I get x of n minus 1 and x of n. So I get the last one. If you start I equals 0, you go up to n minus 1, and this will be the form. Now, what we're going to do in the last video, I'm going to set this up. We're going to do an example of this now. Here's an important theorem, though. If a function is continuous on a closed interval, then the endpoint and midpoint approximations, and when I say endpoint, I mean left or right endpoints, they approach one and the same limit as n goes to infinity. You remember I was looking at the table of Rn and Ln for our example, how the values were getting closer and closer to each other? Well, in fact, as n continues to get bigger and bigger, and we say what? Take the limit as n goes to infinity. I hope you remember limits at infinity. Of each of these quantities, the right hand, left hand, and midpoint, they're all going to equal a fixed number L, okay? And if f of x is indeed greater than or equal to 0 on that interval, then we define the area under the graph of that function, the area under the graph and above the x-axis over this interval, to be equal to this limit. So that is the exact value of the area. The exact value of the area. Okay? And so we'll look at these power sums in the next video, and we will look at an example, our first example of actually finding the area now with this process.